Angular momentum of a rigid body under complex motion, meaning rigid body under translational plus rotational motion, which can alternately be viewed as translational motion of center of mass of the rigid body plus the purely rotational motion about an axis passing through the center of mass. So how do we approach such situations? Let's begin with the definition of angular momentum of a system of particles about a point, say O. Well, angular momentum of a system of particles about a point is defined as sum of Ri cross Pi, where Ri is the position vector of the ith particle from the given point O and Pi is its linear momentum. Now, if we were to write this position vector Ri as position vector of center of mass with respect to O plus Ri dash, where Ri dash is the position vector of the ith mass from the center of mass, then we can rewrite angular momentum about O as RCM cross P system plus Ri dash cross Pi, where P system is the linear momentum of the system, which is simply mVcm, and Ri dash cross Pi is the angular momentum of the system about its center of mass. Note that we have used Vi, that is velocity vector of the ith particle, with respect to an observer on the ground as Vcm, that is velocity vector of the center of mass with respect to an observer on the ground, plus omega cross Ri dash, which is the velocity of the ith particle with respect to the center of mass. If you are not comfortable with this, recall the concept of relative velocity we studied in kinematics, wherein we said Va, that is the velocity of particle A with respect to an observer on the ground, is equal to velocity of particle B with respect to the observer on the ground plus velocity of A with respect to B. Now let's practice this in the following 9 scenarios. And once again, angular momentum of a rigid body under translational plus rotational motion about a point of interest is equal to angular momentum of the center of mass about that point, that is RCM cross mVcm, plus angular momentum of the rigid body about its center of mass. And note that we are dealing with vector sum here. Now the two important watch-outs in this process are: 1. Correctly determine the angular velocity of the body about its center of mass, which might be tricky when the center of mass is also tracing a circular path. In other words, when center of mass of the body is also under rotation with some angular speed. Here, the knowledge that velocity of any point of the rigid body can be written as Vcm plus omega cross R, R being the position vector of the point of interest in the rigid body from the center of mass. Second watch out is when writing the angular momentum of the body about its center of mass or the angular momentum of center of mass about the point of interest, remember that you are dealing with vectors. So correctly express the angular momentums in unit vector notation and follow the rules of vector addition. With that, let's start with a simple scenario of a disk in pure rolling motion along a horizontal surface with angular speed omega. And let's say that we want to find the angular momentum of the disk of mass m and radius r about origin O as shown. To begin with, let's choose coordinate axis such that x is pointed towards right in the horizontal direction and y is pointed vertically upwards, and z is pointed out of the page or screen. So angular momentum of this rigid body about origin O is angular momentum of center of mass plus angular momentum of the rigid body about the center of mass. That is position vector of center of mass cross mVcm, which will reduce to mVcm r, r being the radius of the disk, minus k cap, minus because direction of momentum is into the plane or towards the negative z direction. And as for the second term, let's note that about the center of the mass, the body is rotating with angular velocity omega, which is equals to VCM by R, given that the body is in pure rolling motion. So angular momentum about center of mass is moment of inertia I times omega, or half mr square VCM by R, or half mVCMR minus k cap. Once again, use the right hand rule to determine the direction of the angular momentum, which is in the negative z direction in the given scenario. So the net angular momentum is 3 by 2 m VCM, that is the velocity of center of mass, times r, the radius of the disk. And the direction of the net angular momentum is towards the minus z direction. Now, before we go any further, let's see what would happen if the center of mass was stationary, in which case angular momentum about any point in space will simply be equal to the angular momentum of the body about its center of mass. So in the given scenario, for a uniform disk of mass m and radius r and rotating about an axis perpendicular to the disk and passing through its center with angular speed omega, the angular momentum about any point in the space, say O, will be ICM, that is the moment of inertia about center of mass, times omega, or half mr square omega in this case. Well, with that, let's move on to next few scenarios wherein the center of mass will be moving along a circular path besides a rigid body being in pure rotational motion about an axis passing through the center of mass. And in the first few scenarios that we will discuss, we will have the two axes of rotation parallel to each other and perpendicular to the plane of the body, making it slightly easier for us to get comfortable with the methodology. And towards the end, we will look at a scenario wherein the two axes of rotation are perpendicular or at an angle to each other, resulting in slightly complex rotational motion about the center of mass. So let's begin with the scenarios wherein the two axes of rotation are parallel to each other and in turn perpendicular to the plane of the body. And the first two scenarios we will look at here, the angular velocity of rigid body about the center of mass and the angular velocity of center of mass are same. And what does that mean? Well, it means that the rigid body is in pure rotation about a point with center of curvature of every particle of the rigid body centered at the same point. With that, let's look at three scenarios wherein angular velocity of rigid body about the center of mass is not equal to the angular velocity of center of mass. Starting with this one, here we have two disks A and B, with disk A held stationary and disk B rolling along the circumference of the disk A as shown. And it is given that there is no slipping, which means that the velocity of point P of the disk B, which is in contact with the disk A at the instant, is 0. And since we can write the velocity of any point of a rigid body as the vector sum of the velocity of its center of mass and cross product of omega about the center of mass and position vector of that point from the center of mass, we will get omega about the center of mass as 2 omega. Afterwards, we just need to use the relation LO, that is the angular momentum of the rigid body about O, equals to RCM cross MVCM plus angular momentum of the rigid body about the center of mass to find L about O, that is the angular momentum of the disk about point O. Moving on, in this scenario, we have a rod of mass m and length a and a disk of same mass m and radius a by 4. Rod is hinged at point O, while disk is hinged on the rod at a distance of 3a by 4 from O as shown. And rod is rotating about O with an angular velocity omega, and disk is rotating about its center of mass with angular velocity 4 omega as seen by an observer on the ground. Here, the angular momentum of the rod disk system about O is simply sum of angular momentum of rod about O and angular momentum of disk about O. Now, magnitude of angular momentum of rod about O is simply its moment of inertia about the z-axis passing through O times omega, which will simply be 1 by 3 ma square omega, with the angular momentum vector pointed along the positive z-axis. As for the disk, we can use angular momentum of disk about O equals to RCM cross mvcm plus angular momentum of the disk about its center of mass to find the angular momentum of the disk about O. Moving on, in this next scenario, we have a massless rod hinged at O at one end and a disk of mass m and radius r mounted at the other end, with the plane of the disk perpendicular to the rod as shown. And it is given that the disk is rotating about the rod with an angular velocity omega dash, while the rod is rotating about the vertical axis passing through O with an angular velocity omega. And we are interested in finding the angular momentum of this system about point O. Well, we will use the relation the angular momentum about O of the disk equals to RCM cross mvcm plus angular momentum of the disk about its center of mass, where RCM is A I cap and VCM is omega A j cap at the given instant. Now, as for the angular momentum of the disk about its center of mass, let's first establish the angular velocity of the disk. So note that omega dash is the angular velocity of the disk about x-axis, but what about the angular velocity of the disk with respect to center of mass about the z-axis? Well, that is omega. But how do you determine that? Well, you can do so algebraically using velocity of point B is equals to velocity of its center of mass of the disk plus omega cm cross r, like we have done in some of the previous scenarios. But the involved math might seem tricky. Alternatively, let's watch the motion of disk along the z-axis and carefully monitor the positions of points A and B with respect to the center of mass. And as you can see, as disk makes one full rotation about O, the line joining AB also makes one complete rotation about the center of mass. So we can say that omega cm is equals to minus omega dash I cap plus omega k cap. Now going back to finding LCM, that is the angular momentum about the center of mass, that will simply be minus ICM about the x-axis times omega dash I cap plus ICM about z-axis times omega k cap, which then gives us the expression for the net angular momentum vector about O. With that, let's move on to the scenario which showed up in JEE Advanced 2016, wherein two disks A and B of mass m and 4m and radii A and 2a respectively are fixed to each other by a massless rod of length L is equals to square root of 24a. This assembly is laid on a firm and flat surface and set rolling without slipping on the surface, so that the angular speed about the axis of the rod is omega. And the question requires you to determine the angular speed with which center of mass of the assembly rotates about the given z-axis, and subsequently determine the magnitude of the angular momentum of the center of mass of the assembly about O, and also determine the magnitude of angular momentum of the assembly about its center of mass. So to begin with, let's talk about the angular speed of the center of mass of the assembly, or for that matter, center of masses of individual disks about the z-axis. Okay, first of all, note that the velocity of center of mass of individual disks is not omega times the radius of the disk, even though disk is in pure rolling motion. Now that might be confusing, as that's what you have studied in pure rolling motion, but remember that in those scenarios, center of mass travels the same distance as the fictitious point at the contact point travels on the ground. Secondly, and more importantly, angular velocity of the disk about its center of mass, and as seen by an observer on the ground, is not just omega along the axis of the rod in this case, but rather vector sum of this angular velocity and angular velocity of the assembly about the z-axis. If this sounded confusing, refer to the previous scenario we had discussed. Now there are two ways we can determine omega dash. In the first approach, let's use the fact that the center of mass and the contact point of the disk with the ground both trace circular arcs and subtend equal angle about the z-axis over a given time period, which will be omega dash times t and should be equal to the arc length traced by the contact point divided by 10a, which will give us omega dash is equals to omega by 5. Alternatively, we can use the velocity of point P, which is the contact point with the ground, is equals to VCM plus omega about center of mass cross RP. RP being the position vector of that contact point from the center of mass or the center of the disk. Something we have been using earlier as well. But note once again that omega about center of mass is not just omega but rather a vector sum of omega whose direction is pointed towards O from the center of the disk, and omega dash which is pointed along the z-axis. So if you correctly write omega cross RP, this will give us the equation as listed here, and on solving we get omega dash is equals to omega by 5. Now as for the angular momentum of the center of mass about O, simply use RCM cross 5m VCM, and as for the angular momentum of the assembly about the center of mass, you can use the scenarios discussed earlier. And note that IIT Guwahati did not expect the students to account for angular velocity omega dash of the assembly about the center of mass when calculating the angular momentum about its center of mass. Similar to previous scenario we had discussed, and is perhaps the reason it treated both the answers correct. That is, one including this angular velocity and the one excluding this. And that summarizes this section. Wish you the very best.